I'm going to be talking about a branch of mathematics called algebraic topology and how it can be applied at analyzing signals. So this is the table of context, is what we're going to talk about, motivation. Then the two use cases are going to be what I call cooperative synchronization of OFDM preambles. Mainly you have an unknown recording and you just want to start demodulating and synchronizing to that OFDM burst. In order to do that, we're going to look at topology, which is a branch of mathematics that helps us study basically shapes and properties of shapes that hold true under nice continuous transformations. Then we're going to look at a recent technique by McInnes called UMAP, which allows us to project data down and do something I call sort of RF surveying. So why look at these techniques? These are mostly unsupervised techniques. And so there's a lot of work being done in automating the creation of DSP components. So at least since the 90s, people have been using machine learning to either write demodulators or classifiers. And very recently, people are working on actually creating transmitting symbols. So writing transmitters. And as these new methods come out, traditional machine learning methods may not be appropriate because you may not have that example in your data set. So it's hard to train a machine learning model of something you haven't seen before. So you're going to have to start thinking about techniques that allow you to analyze data without having seen it. So how do we do that? So this slide comes from a paper from the 1994 by Nakayama, and this is an example of writing an amplitude shift keying neural demodulator. So basically, at the end of the 1980s, they came up with a very efficient method for training neural networks called backpropagation. And ever since then, researchers have been using machine learning to analyze signals since really the early 90s. And so this is an example of sort of a component in a DSP pipeline, particularly a demodulator that's all machine learning based. So they train this neural network to automatically demodulate amplitude shift keying. And another problem that's happening is that people come up with new modulation schemes all the time, either by hand or by committee. And they also just tweak pre-existing things. So you might just take a QAM and just rotate it, and all of a sudden that's your new constellation diagram. That may not be in your training set, that may be in your training set, but it's in the real world. And signals oftentimes look radically different under noise. So if you're not going to clean up the signal prior to putting it in your machine learning algorithm, and you're not going to train on some sort of channel, you're going to have to deal with these different kinds of noise. And what's also important is that although this is noisy, there's still information, right? So if you kind of can guess at the constellation, you can still pull data out of it by basically isolating the rings, right? And you can create sort of an equivalence class saying, you know, these are these bits, those are those bits, and those are these bits. You would only get 3 bits of information here, but that's better than nothing. And so this is what I was mentioning now, is that people with basically very little code can start creating their own modulations that are optimized depending on a noise model. So this is using sort of what I call pseudo TensorFlow. If you actually run this, it won't run. But this sort of gives you a sense of how easy it is, and this is stuff done by Tim O'Shea, on how easy it is to use autoencoders to generate new constellation diagrams where you input your noise. And people even get more crazier, so now DeepSig is automatically synthesizing transmissions of signals into space and creating DSP pipelines completely automatically optimized. And that's definitely not going to be in your training set when you start applying machine learning algorithms. And if it is, then you're very lucky. But then again, these new algorithms these new modulations can pretty much appear at any time. So how do you deal with this? How do you deal with data you've never seen before? So this is sort of the problem statement of non-cooperative synchronization and demodulation. We'd like to write a program that doesn't have a lot of assumptions. It's going to have some assumptions, it has to know something. And we'd like to be able to sort of feed in data and get sort of bits out. So these assumptions are going to be, we know the sampling rate, which is a big assumption. I'd be interested in talking about methods of automating that. I don't think that's too hard. And then we're also going to assume it's using some sort of FFT, IFFT-based modulation, so in this case, OFDM. But we're not going to assume that the preamble doesn't necessarily have all the aspects of OFDM, right? So it may have a cyclic prefix. It may not have a cyclic prefix. It may be, for example, cyclically delayed encoded. And so we're not going to assume that. We're just going to assume we have some sort of FFT, IFFT-based modulation. So here's just some example data from the real world, and we're going to now synchronize to it. Traditional methods of synchronization, these are some of them. I've tried to order them by what I call most assumptions, right? Energy is just, I detect more energy than I've seen before, and you sort of have a ratio, and you just do a division. And you don't really assume a lot about the signal, right? You have sort of delayed conjugate multiply methods for OFDM, but that's going to assume some sort of repetition, mostly in the cyclic prefix. Then you have more, I guess, neater methods based on sort of standard deviation. So you know the cyclic prefix, you know the FFT, and what you basically apply that FFT on different windows of time. And if you apply it in the right window, your standard deviation is going to be a lot lower than if you applied it in the wrong window. Because if you know anything about the FFTs, when you do that, you're going to get a phase distortion if you're off in time in the frequency domain. You can also look at more statistical properties, periodic statistical properties. Your preamble, the last two basically assume you know the structure of the preamble. The preamble was designed specifically with a particular structure, and you can synchronize using that structure. And in the extreme case, you just know the data in the preamble, you know everything, you just cross-correlate against it. But in non-cooperative settings, you know none of this, right? You just have a device, you have the signal, and you need to recover all these parameters, and you have to figure out a way to do that. So there's sort of a paradox in a sense where in order to recover the signal, you have to clean the signal, but to clean the signal, you kind of had to know what the parameters of the signal were. This is normally not an issue, right, if things are designed by committee, because the transmitter and the receiver already know what's going on, and they're designed. But if you don't know, it gets really hard when you start reverse engineering. So this is where I think topology can play an important role in aiding sort of the automatic signals analysis. So what is topology? You can think of topology as a way of approximating space. In this case, we're going to be talking about point clouds, much in the same way you approximate functions, like in a Taylor series. But in this case, we're going to be approximating the space by sequence of vector spaces and linear maps between them. And so how do we create these vector spaces? So we're going to take the space and we're going to triangulate it. So we're going to create a combinatorial object. And this combinatorial object is going to be sort of decomposed into these constituent objects that have analogs in higher dimensions, but in our cases, we're just going to think about points, edges, triangles, and tetrahedron. And basically, we're going to take our point cloud and glue it together with a whole bunch of these things. And we're going to create something called a simplicial complex, which is just a series of nicely glued edges, points, and tetrahedron and higher analogs. So there's another way we can get a combinatorial object. So if we want to study the circle combinatorically, we can basically put these little open sets, take intersections between these open sets, and we get sort of this corresponding regular polygon. And that's also a way of studying the circle. You can study this now looking at the points, the nodes and the edges, as opposed to all the continuous information contained in the circle, and you can derive some properties. So going back to this way we're going to approximate spaces, we're going to take a simplicial complex. I'll show you how to do that and create it from data, but let's just assume you are given a simplicial complex. We're then going to create basically vector spaces that are vectors, Boolean vectors. I don't know if this is a pointer, but Boolean vectors that are formal sums that indicate like what the points are. So like let's say this point at the very bottom would have like a 1 in the first spot and zeros everywhere else. You're going to have the second point right next to it. It's going to have a 1 in the second spot. Everything else is going to be 0. And you do that for all the points, right? So now you have all these little vectors that are Boolean. Same with these edges, and same with the faces, and same for this tetrahedron. We're basically going to create vectors for each one of these objects. And then we're going to have linear maps between these objects. And using these linear maps, you can compute properties. And the properties you can compute are things like connected components. So that would correspond to like how many points you have in your constellation diagram. So if you have 2 connected components, it's like a BPSK type of thing. 4 connected components, right, and so on. So how do you actually get this with data? So this is a very, very nice slide coming out of a paper on, it's hard to find really pretty pictures that describe this. So a lot of people put in a lot of work. This is not mine, but the references are at the end. But so what happens if you start off with data, sort of these points, you put a little circle around each of the points, and you look at intersections of all these circles. And this axis here at the very bottom is the radius of that circle. And these H1 and H0 are what they call homology groups, but they basically are counting different properties of the space. So H0 is going to be counting the number of connected components, and H1 is going to be counting the number of circles. So in the very beginning, all the points are separate because they all are their own little islands. And as we increase epsilon, namely the radius of the circle, you see that some edges start to merge and they're no longer existing. And in particular, the circle is really important because at this point right here, you can see that a circle forms in this diagram but then disappears. And we have a persistent circle, and that's what this line is indicating here. And we have a persistent connected component, because once all the radiuses get big enough, all the points are connected. So there's just one giant blob at the end. But you also see we capture the fact that we're looking at a circle, a noisy circle from the very beginning. So there's another way of creating these objects. This is called the mapper algorithm, where you take your point cloud and you have some sort of summary function on the point cloud. This is hard to see, but when you have a summary function, you cluster in that space, and then you take the inverse image, and you take intersections of the result, and you form a graph here. So it's another way of organizing the data. This is a much better picture of the output that you get. So you imagine you start off with a whole bunch of vectors. You have some sort of summary function. It doesn't have to be an R. It gets a little bit more complicated because you have to cluster in that space. So if it's just R, it's a little easier. You cluster in that output space. You look at the inverse image of those clusters, and then you group those together, and you form this graph. And this graph can tell you a lot about what your data, what are outliers. It can really present the data that would otherwise be very hard to visualize. And so going back to our DSP example, we'd like to do these techniques and hopefully extract some meaningful information. So what we do is we take multiple sizes of FFTs, we slide them across this recording, we look at the variance and the entropy to pick the right FFT size, and once we have the right FFT size, we slide it across again, and we see that this is the start of the burst right here, and same here, this is the start of the burst right here. And we'd like to extract data. So normally what you would do is you'd clean up the signal, right, and you'd orient everything correctly. You could do that from this data because you know the phase shift because you're off. But this algorithm is instead just going to directly demodulate that data. So how do we do that? Is that we use a method called topological mode analysis. And this graph right here is the same graph as I was talking about before with all those lines called a barcode diagram. And this is indicating that we have two strong connected components. So basically, these two things are persistent. And so if we do these methods on this data, we can actually extract exactly what the start of the burst is and demodulate this data. Now, I call this a fuzzy demodulation because, it's rotating in space constantly. And so your zeros might be ones and your ones might be zero, and you might have some sort of error. But at the same time, you're extracting data that you otherwise wouldn't get. And if you do that enough times, you can start to get after what the sync preamble is and what the data actually contains. And then you can go back to these more traditional methods once you start writing the receiver. So another use case for topology is an automatic modulation classification. So in the previous talk and in the keynote, it was discussed where you need a training set. You have to train this machine learning algorithm. And also in the keynote, there's a lot of things that we don't have demodulators for. So if you have a database of signals, how do you visualize the structure contained in that database? And so automatic modulation classification may be one way to do that. Two main approaches for automatic or two main reasons you would do it is one is you want to sort of automatically infer the rate of encoding that you do based on the channel. And then the other use case is extracting information, like in this case. So this is, again, coming from the book by Nandi and Xu on automatic modulation classification. Same with this. So this is talking about classifying 10 different modulation schemes using various methods. All these methods, though, are supervised in the sense where you already had a priori knowledge of the database of possible signals that you would see. Some of these methods actually require more information, like the maximum likelihood method actually requires you to know the SNR that things are generated under. So that's not always readily available to you. So unsupervised machine learning can help in this case as well. So supervised machine learning was like in the last talk where you'd have a whole bunch of signals, you can have some features, and you would train a machine learning algorithm. Unsupervised approaches do not require you to have labeled training data in order to extract structure. And reinforcement learning is another approach to machine learning. You may have heard about it in Google's AlphaGo, but we're going to be talking about unsupervised machine learning. So if you applied unsupervised machine learning, this is one way you could do that. So what you're looking at here is 10 different modulation schemes from 2PAM up to 256 QAM. And there's a vector of 1024. There's about 10,000 instances of each one. And so you have a matrix that's dimension 1024 by 10,000 times 10. And we'd like to visualize that structure. And if you use sort of the go-to method of doing this, t-SNE, you don't get a nice tight clustering. And it also takes a very long time to do this computation, which is I think, very important for this kind of stuff. So this will take on the order of like 10 or 15 minutes to compute. But on the left-hand side, if you use McKeon's UMAP, you get this in a couple seconds. So I think that's very impressive. So what is this method, and why is it cool? So this is coming from the GitHub documentation of UMAPs, which you should just go clone right now and play with because it's awesome. And so what happens is that normally when we do the radius method to compute the simplicial complex, there's a problem if the points aren't close together and you don't have a nice uniform radius. So if we do this method, take the intersection, you can see there's gaps here. And that's not very good for approximately representing this space. So another method that he came up with, this was very clever, was making two simplifying assumptions. One of them was that the space is all connected. And another one is that they are very close together in the higher dimensional space. And so when you do that and you use k nearest neighbors as opposed to just radius space intersection, you end up getting this very nice approximation of the space. And so we can do this, but instead of these points on 2 dimensions, we can do this on the 1,024-dimensional space, construct a simplicial complex, and then McKeon's also come up with a method of basically projecting that simplicial complex onto lower dimensions, which is the output of this. And, and the performance is very good. Again, this is from his GitHub page. It's very impressive. So if you're familiar with PCA is like the go-to method for doing these kinds of projections. It's also very, very fast. And you see UMAP is not as fast as PCA, but it's certainly much faster than t-SNE. And so these are the results again. And so if you wanted to use other methods, you could use this output and train, let's say, a neural network to produce similar output. And so you could do this sort of automatic modulation classification using this kind of output. Another application of this is like surveying the RF spectrum. So if you don't know everything that exists in a location that you're at, but you kind of want to present that information in a more palatable way, you could sort of project this information in any dimension. 2 and 3 are probably the best bets for us. But if you're an alien, you can see like higher dimensions. But like this would be a way to organize sort of the universe of signals that you're collecting. And yeah, so that's basically it. Just these are 2 sort of techniques. Usually in DSP, we sort of divide things mathematically: statistics, linear algebra, complex analysis, real analysis. But there's a whole other view, right? There's a view of geometry and a view of algebra. And I think using these tools are like telescopes to look at the world, and they give you a different perspective on digital signal processing and the kind of data that exists out there. So thank you very much. I don't know how much time I have.
All right, Raphael, thank you. Okay. All right, do we have questions from the audience? Yeah, a few. Where's the other handheld, by the way? Do you have that?
Hi. You mentioned choosing the FFT size based on entropy, something like that?
Yeah, so what you do is you create a graph where I didn't show this, but you create a graph where you have multiple FFT sizes that you use, right? And then on the x-axis is the offset at which you applied that FFT, and on the y-axis is your measure of dispersion, variance, entropy, stuff like that. And what you see is when you do that, the point of minimum entropy or the point of minimal dispersion will correspond to the right FFT at the right offset. And so once you do that, you figure out the FFT size, and you kind of reapply that to the signal, and you can use these sort of clustering based approaches. I mean, I called it topological mode analysis. That's from INRIA. That's their method of doing clustering that uses the topology of the data to infer the number of clusters. So you don't have to use that as a parameter. So if you were to use like k-means or something, you'd have to pick k, which kind of defeats the point, because then at that point you already know what you're looking for. This allows you to do that.
Thank you.
Other questions? No? Okay. Thank you very much, Raphael.